Electricity contributes to advances in science, medicine, and technology, helping to improve our quality of life. Working for us every day, in our homes, on our jobs, while we relax and play. Union Electric Company is pleased to bring you this program as part of our continuing community service activities.
Windmills. They were a technological breakthrough when first developed back in the 18th century, and they're still being used today. Windmills are able to respond to the slightest changes in wind direction. A small gust, and the cogs and wheels are set in motion. By sensing varying wind patterns, the fan wheels on the back of this windmill adjust to keep it working efficiently. It responds only to the wind, not the sun, rain, temperature, or anything else, just the wind. That's the secret of a sensor. It reacts to one particular thing. Sensors come in many forms, some natural and some man-made. In fact, science and industry have developed sensors for and from everything imaginable. In this edition of Science Screen Report, we'll focus on the importance of sensors in everyday life. See how they're being used in medicine as biosensors, in space, aboard satellites, underground, to detect evidence of nuclear waste, offshore, for seabed profiles, and in the air to document the effects of acid rain. Sensors, they are all around us. Some have electric eyes, some touch and measure, others taste and smell. Here, sensors act like electronic bloodhounds, designed to detect the earliest traces of spoiled meat. Our own senses of sight and smell are crude in comparison. To determine whether or not this beef is fit for human consumption, something much subtler was needed. Taking this into account, chemists and engineers designed a sensor that records the chemical changes that occur in the fat and flesh of meat as it ages. This sensor is fitted with 4 electrodes. Acting as a probe, it measures the level of glucose at different places in the meat. If the meat is suitable for consumption, the electrode signals the computer to indicate a gently sloping line. If the meat is spoiled, the reading shows a sharp gradient. It's a simple sensor, but it could protect lives and the economy. Cattle supply other elements of our diet as well: butter, cream, and cheese. All of these products come to us with the help of sensors. Sensors attached to milking clusters determine a cow's productivity. They measure the amount of estrogen in her milk, which indicates fertility. Sensors can even detect the earliest stages of disease. Sensors save the dairy farmer both time and money. In our next example, sensors save lives. In southern Africa, millions of acres of land lie unused because of the notorious tsetse fly. The tsetse is a deadly insect that inflicts sleeping sickness on both man and animal. What might have been perfect pasture becomes a death trap for the oxen the tsetse feed upon. To help eliminate the tsetse's threat, scientists began numerous experiments to attract the flies and kill them. What they needed was bait. As the flies were obviously attracted to oxen, they decided to bait their traps with ox odor. It worked. Tsetse flies were captured from miles around. The next step was to find the attractive element in the ox odor so that the scent could be synthesized. Using a powerful microscope, a man-made sensor is slipped onto a real-life sensor, in this case, the tsetse's antennae. Now scientists can record when the fly senses a smell it really likes. By using a method called gas chromatography, researchers record the effects of ox odor on the tsetse's delicate antennae. Gas chromatography sorts out all of the molecules in the ox cocktail by weight. The machine then blows a single molecule across the tsetse's nose every 15 seconds. When the fly likes the smell, its antennae respond, and the man-made sensor picks up the signal. The more it likes the smell, the bigger the response recorded on the printout. After months of research, chemists uncovered the chemical composition of the oxen odor. By mixing octanol and acetone in equal parts, they were able to synthesize the odor and utilize it in tsetse traps. With the help of sensors, this special oxen cocktail could open up a new way of life for the hard-pressed people of southern Africa. Every sensor is developed with a particular task in mind. In our next example, sensors become mini chemistry labs. These tomatoes are grown using a technique called hydroponics. The method doesn't use soil, yet it increases crop yield by about 200%. Aerated water mixed with nutrients continually bathe the roots of the plants. To ensure proper growth, the nutrient mixture must be exact, or the tomato plants will die. Primed and calibrated, sensors correctly measure and relay information on chemical composition via microcomputer. This constant checking system keeps the flow of nutrients at the right concentration and free from poisonous levels. But as fantastic as sensors may seem, they can only monitor very simple reactions. One sensor for one reaction. Complex processes remain unsolved. Some of the most complex sensors have been developed by chemists. These sensors are called biosensors. Biosensors are devices in which biological components, plant or animal tissues, are joined with instrumental components, often electronic, to form probes that can rapidly and selectively detect or measure particular biochemicals. Substances subjected to these biosensor devices include drugs, metabolites, pollutants, toxins, and other biochemicals. In searching for biosensors, chemists try to find two chemicals that react to one another. This reaction will indicate the presence of a particular chemical. Sodium and oxygen are perfect examples. Sodium is inescapably drawn to oxygen. In fact, the chemical attraction is so great and so specific that the result can be explosive. Scientists want to build up a library of chemicals which are tailor-made to monitor any biological process. They're trying to find a chemical that locks into another specific chemical, like a key would fit a lock. Then they'll search and design a whole range of keys. Each key, when fitted to the tip of a probe, will search out, identify, and quantify just one lock. In other words, each probe or sensor will seek just one chemical or molecule amidst thousands in a chemical soup. Already progress is being made, but when you're searching for a needle in a haystack, finding one molecule out of billions of molecules takes time. If doctors knew the exact amount of carbon dioxide that a patient under anesthesia exhales, they in turn would be able to use less gas. This would make surgery requiring anesthesia much safer. This sensor, when perfected, will do just that. But as well as looking for naturally occurring biochemicals, chemists are also designing others that will detect a specific chemical. For instance, hydrogen sulfide. You may recognize it if you've ever smelled rotten eggs or stink bombs. Actually, hydrogen sulfide is a deadly poison and an explosive, a particular danger to miners. Miners used to detect the presence of hydrogen sulfide by lowering canaries into mines. Too much hydrogen sulfide and the canary died. Today, a chemical biosensor takes its place. Currently, the analytical sciences are experiencing the biggest sensor boom. With the aid of a computer, sensors provide real-time, on-site information about the presence and concentration of chemicals in a certain environment. As a result, they can often eliminate the need for sample collection, sample preparation, and later analysis in a lab. These advantages, in turn, can aid the development of cleaner, more efficient industrial processes and more effective environmental cleanup efforts. By turning these grains of sand into translucent glass fibers, we have a tough, flexible material capable of transmitting light along its path. These fiber optic sensors are coated with a chemical that changes color when it meets another specific chemical. This sensory device is a simple way of identifying the presence of specific molecules. Fiber optic sensors are indispensable due to their ability to transmit information from hard-to-reach places, like inside the human body, to the deepest oceans. Phonograph pickups often contain crystals which act as piezoelectric sensors, converting the mechanical vibrations of a record into electronic signals. New advances in polymer technology apply the same principle. In theory, piezoelectric plastics could serve as underwater sails to transform the vast and ever-present mechanical power of ocean waves into electricity. Piezo-based sensors are also being used to detect volcanic activity and other movements in the Earth's crust. Some sensors respond solely to heat. Within this aerial observatory is a remote sensing system capable of locating forest fires and simultaneously transmitting the information to firefighters on the ground. Via satellite, NASA uses remote sensing techniques to zoom in on delicate ecosystem boundaries. Ground stations decipher and manipulate this data into photographic images, collecting detailed information on all aspects of the environment. From mapping to robotics, sensing devices are becoming increasingly sophisticated and complex. At the Jet Propulsion Laboratory in Pasadena, California, simulations are underway with a robotic gripper capable of transmitting a sense of feel to its user. This unique system is being explored using a specially sensored helmet and glove. Other breakthroughs include a sensory device designed and built for autonomous cross-country vehicle operation, and an underwater sensor for determining important characteristics of the seabed without drilling and causing possible harm to the marine environment. While the intricacies of the human sensory system may still amaze us, science is catching up with sensor technology, refining each of the senses and pushing them to perfection. From diabetic insulin pumps, which sense and release the correct dosage of glucose, to ensuring safe, accurate satellite docking procedures millions of miles away, sensors are making our lives richer, more satisfying, and are helping us reach into the future.
This program has been sponsored as a public service by Union Electric Company, serving more than 1 million customers in communities throughout Missouri, Illinois, and Iowa.